那我们今天要讲一些跟线性代数有关的应用。那这个应用有分成几大类。首先，第一大类呢是所谓的 computer graphics. Today we're going to go over some application of linear algebra. The first class of application is computer graphics. So the first example is that we can actually express some graph using a giant matrix. So in this example, we have a letter N, capital N, and then this letter N has 8 points or 8 vertices. So we can express the coordinates 坐标 by the 8 columns of a matrix. So the first columns correspond to the first vertex, and then the second column corresponds to the second point. The third column corresponds to the third point. Fourth column corresponds to the fourth point, and then fifth column corresponds to the fifth point. Sixth column corresponds to the sixth point. Sixth column corresponds to the coordinate of the seventh point, and the eighth column corresponds to the coordinate of the eighth point. And then we call it a D. Then it can be used to represent such a graph. And suppose we want to do some transformation, change of the shape. So we are given some matrix, and then we can describe the effect of the shear transformation on that letter in the example. So in order to have the shear effect on that previous capital letter N, 就我们要对刚刚前面所出现的那个 N 来做一个推移的转换变形，那我们就可以在 D 的那个前面我们定义的那个坐标所组成的 matrix 的左边组成一个 shear matrix A。那这个 A matrix 是这边给定的，它的作用是 shear。So we can left multiply the matrix A, and then that matrix A will functioning as a shear transformation. And also we can continue to do the linear transformation on that capital letter N. So suppose we want to compute the matrix of the transformation that performs a shear transformation as in example 2, and then scales all coordinates by a scalar of 0.75. So we see the result effect is that this capital N is still under the shear transformation, and then it becomes thinner, 变得比较长, becomes taller. Then this effect is to multiply the coordinate of a point by multiplies the x coordinate of a point by 0.75. And then the transformation matrix should be like this, the standard matrix to multiply all x coordinates by 0.75. So it looks like this. We have 0.75 on the first rows because that corresponds to the x coordinate. 第一个元素对应的是 x 的坐标轴。And then we again left multiply S matrix on the A matrix. 对 A matrix 左乘 S， 那意思就是说把原本的 A 矩阵的转换之后，就 A 是做 shear 嘛，前面我们在第二个 example 的时候，这个步骤是 shear。然后呢，接下来要做一个scaling。那先做的那个是放在左手，先做的那个放在右手边，那你后做的那个动作要在左乘它，所以会得到一个集合的matrix。那再把这个集合的 matrix 再一样是用刚刚前面的 D matrix， 就是包含8个点的那个 matrix 左乘 SA 这个结果的 matrix， 那么就会得到像 Figure 3这样子的效果。所以 computer graphics 里面的一些效果，它都是用矩阵运算来操作的。Okay, then now we introduce a concept called homogeneous coordinates. 我们要介绍一个叫做 homogeneous coordinates 的概念。那它的概念是说，假设我们一开始只在一个二维的平面上面操作点 x y， 那现在因为我们要做一些平移跟旋转等等的 transformation 的动作，所以其实我们需要一个三维的空间才有办法去对。例如说，我们可以把它做升降，原本是 x y， 它只能够在平面上移动，就它本身已经是一个平面了。那如果我们要进一步去移动它，我们其实需要一个第三个维度，就多一个维度，你才有办法，就好像说我们真的那个在一个 box 里面，然后去调整某个平面，那你才能够去做升降的动作。OK，那这个新加的这个坐标这个维度呢，被叫做 homogeneous coordinates。你可以想象说它是一个辅助的功能。Okay, we say that x, y has homogeneous coordinates x, y, 1, where 1 is an additional coordinates. And this is for the purpose to operate the shape, the graphics in a two-dimensional plane to be able to be lifted up or drop it down. So we need an additional dimension so that we can operate such changes. So for instance, the point origin 0, 0, we want to have a homogeneous coordinates, which is by adding an additional dimension and then put 1 at this position. So 0, 0, 1 is the homogeneous coordinates of 0, 0. So a homogeneous coordinates always have one more dimension than the original point. And okay, so we can see the example. Suppose we are consider a translation. Translation is something we defined last time on Tuesday. Translation is parallel shipping. We're shifting, parallel shifting. So we're moving a parallel plane. We're moving a plane parallelly, and this is like a translate the plane by p by adding this constant. So this procedure is called translation. So we'll consider a translation from a translation of the form xy to x plus h and y plus k. And then we want to write this point xy, this translation on a homogeneous coordinates. So both of xy and x plus h and y plus k need to add an additional dimension and then put 1 in that position. So xy becomes xy1 and x plus h and y plus k becomes x plus h, y plus k and 1. It becomes three-dimensional vector so that we can the purpose of adding this is that we can move it, shifting it through the third dimension, which is the homogeneous coordinate. And this transformation can be expressed as the matrix form. So we are having a matrix like this, and then it's left multiply xy1, which is the input vector, by this matrix. We will obtain the output vector like this, and this is the output vector. And so any linear transformation on the R2 can be represented with respect to homogeneous coordinates by a partition matrix of the form. So this is exactly the same thing we were continually talking about. So originally we have a transformation matrix A, and then to put this matrix in a homogeneous coordinates, we add one more dimensions by adding a single value 1 in the diagonal elements, and then the remaining rows and columns elements are 1。那这个是我们把一个 A 矩阵，它原本是假设 A 矩阵是一个2×2的矩阵，那我们要把它放到一个homogeneous coordinate 的方法，就是把这个矩阵变成一个3×3的矩阵。那变成3×3矩阵之后呢，我们在 diagonal elements 的地方放1，然后其他位置放0。那如此一来，这个矩阵就是处于一个 homogeneous coordinate 的状态。OK， 那 example 就是说，我们现在有一个 counterclockwise rotation about the origin with angle phi 这样子的一个旋转矩阵。然后呢，我们把它放置于coordinate homogeneous coordinate 的时候呢，这个矩阵就变成一个3×3的矩阵。那前面就是有讲过说，为什么我们要把它变成一个3×3矩阵？因为就是方便在 computer graphics 的领域中可以做操作。So we are putting the standard matrix of a counterclockwise rotation about the origin with angle phi on the top left corner, and then add a diagonal element 1 with all the other elements being 0, and it becomes a 3×3 matrix. Similarly, in order to create a homogeneous coordinate standard matrix, we start with a 2×2 matrix. And then by putting this matrix representing the reflection through y equals x line, and we add a diagonal element being 1, and then the remaining 2 elements becomes 0. And next, this is a 2×2 matrix representing scaling x by s and scaling y by t, a scaling matrix. Then we can do the same thing, which is by adding a diagonal element 1, and then the remaining positions we put 0. Now you see 3 matrices representing its own linear transformation, and then it's on the homogeneous coordinates. Then we can start to describe how to perform the composite transformation. So the movement of a figure on a computer screen often requires more than one, 2 or more basic transformations in order to show the show the graphs like more like real things. The composition of such transformation will correspond to matrix multiplication when homogeneous coordinates are used. So they are not just doing the linear transformation consecutively. They also need to perform that linear transformation on the homogeneous coordinates. Okay. So the next example asks us to find a 3×3 matrix that corresponds to the composite transformation of a scaling by 0.3, a rotation of 90 degrees about the origin, and finally a translation that adds this vector to each point of a figure. So we're actually compositing 3 transformations, and with the first step 1, this scaling, step 2, rotation, and then step 3, translation. We need to do 3 of them, and then we need to perform it on the homogeneous coordinates. So what we are working on is the vector x, y, and 1. And why is there's a one value here? 为什么这里会有一个1？那因为我们现在是要在 homogeneous coordinate 这样子的一个人造的坐标轴上面去做操作， So the reason why that we are actually trying to transform the shape originally on a two-dimensional plane xy vector, and then try to find the new vector x prime y prime. But then in order to make the translation operatable, like doable, so we need to create a homogeneous coordinates to add one more elements in it in its third dimension. OK，那我们在第三维度加了一个一之后，我们就有办法在 homogeneous coordinate 上面做操作。那 scaling 的动作是对应到这个矩阵，前面我们有看到过。为什么 scaling 是这个矩阵呢？我们可以看一下，就是 scaling is this matrix. This is scaling matrix. 那这个是 reflection matrix. 那这个是 rotation matrix. 那这三个 matrix, these three matrices are on homogeneous coordinates. 所以它是三维的 so that they looks like a three-dimensional 3x3 matrix other than just 2x2 coordinate. Okay, so this is we're using the third scaling matrix as the first step in that example we have just seen. So in this example, the first step we should do is to scale 0.3 for both x and y axis. And this one becomes the same thing right here. So basically that's the first step. And the second step, we need to do the rotation. So here the rotation is 90 degree. So we need to use the cosine and cosine phi, sine phi, and negative sine phi and cosine phi, this matrix to do the job. So that becomes the second step, rotate 90 degrees. And then the third step, the question asks us finally a translation that adds negative 0.5 and 2 to each point of a figure. So we're translating it parallelly. And be careful about how we're going to do that translation. That translation is added right here. By adding the negative 0.5 and 2 at this place, and then we can reach the ultimate goal, which is to translate the graph with this amount of values. So now you can probably see like why we need the third dimension, because it allows the translation happens. We can allow we can perform a translation like this. Without the third dimension, we are unable to add values right here. Okay, so here's a graph like showing the process we have a original figure, and then we scale it by 0.3. It becomes a smaller figure. And then we rotate 90 degrees. So it becomes a arrow pointed to the left, 变成一个向左指的一个箭头。And then the translating is moving it with a point move up and move to the left with a point negative 0.5 and which 2 negative 0.5 and 2 translation. So with the homogeneous coordinates, we are able to change the shape of the graph. So what will be the compositive transformation? Compositive is 集成的, is to multiply all the matrices together. So we're have the step 1 scaling to be put on the very right, 放在最右手边. And then the step 2 is to do the rotation, and step 3 is to do the translation. Eventually, we multiply all 3 matrices together. We get one single matrix in this format. Okay, so there are similar ideas for the 3D coordinates. Basically, in order to operate a 3D case, we need to add the 4th dimension to it. So for example, x, y, z, 1 are homogeneous coordinates for the point x, y, z in R3 space. We simply just need an additional dimension to operate, for us to operate the computer graphics. And here it says that generally x, y, z, h are homogeneous coordinates. For x, y, z, if x and capital X has this relationship, like x equals to capital X divided by h, y equals to capital Y divided by h, and z equals to capital Z divided by h, it's better to look at the numerical example. So I have this one, which is 4-dimensional, and it says that it is a homogeneous coordinate for 5, 3, and 7. So it has homogeneous coordinates. The most straightforward homogeneous coordinate is 5, -3, 7, and 1, right? But here it says that 10, -6, 14, and 2 is also a homogeneous coordinate. Similarly, -15, 9, -21, -3 is also a homogeneous coordinate for 5, -3, and 7. So the reason why all the three of them are homogeneous coordinates is because they satisfy equation 1. We can tell that x, the lower letter x, is equal to capital letter of x divided by h, like 10 divided by 2 equals to 5, and then -6 divided by 2 equals minus 3, and then 14 divided by 2 equals 7. So therefore, this one is a successful homogeneous coordinate. It can be used as a homogeneous coordinate. And right here, I have minus 15 divided by minus 3 equals 5. And then 9 divided by minus 3 equals minus 3. And then minus 21 divided by minus 3 equals 7. So this one is also a good homogeneous coordinate. So here it says that with the homogeneous coordinates, we are able to use 4x4 matrix and then to operate a 3D figure like this. So this is a 3D figures. But then in order to do the translation, transformation including translation, then we need a 4x4 matrix to operate on it. So I'm going to skip some of the process to like discuss about like how we're going to create that matrix. But as a result, the matrix for rotation in the homogeneous coordinates is a 4x4 matrix like this. And you will see that there's a diagonal element added here, and then the value is 1. For the remaining part, we put 0 right there, and then it becomes a 4x4 matrix, a rotation matrix for homogeneous coordinates. And here it says that we can also do the perspective projection. A 3-dimensional object is represented on a 2-dimensional computer screen by projecting the object onto a viewing plane. So we're doing projection. For simplicity, let the XY plane represent the computer screen, and imagine that the eye of a viewer is along the positive z-axis at some point 00D. A perspective projection maps each point xyz onto an image point x star y star 0, so that the 2 points and the eye position called the center of the projection are on a line. So we are doing such a projection. We are projecting this point to x star y star 0. So it's like the projector, and then this is the large screen that can project the image. And then the center is right here. This is center 00D. And then we can use the similar triangle properties, 利用相似三角形的性质 to find out that, okay, x star and x has this relationship, y star and y has such a relationship. And then again, we need to use a homogeneous coordinates. We can represent the perspective projection by some matrix. Basically, we want to XYZ1 will be mapped into x star, this is x star, y star, 0 and 1. And scaling these coordinates by 1 minus z over d. That's what has been doing during the projection. We can also use x, y, 0 and this 1 minus z over d as homogeneous coordinates for the image. So now it's easy to display P, and then P has such a P is the matrix to do the perspective projection, and this matrix has this format. And you see, like roughly observing it, we can see that, okay, I have 1 1 0 1 here, and then there is a minus 1 over d being added to this position. And then with that matrix, let S be the box with vertices 1, 2, 3, 4, 5, 6, 7, 8. So this is a box that contains 1, 2, 3, 4, 5, 6, 7, 8 vertices. So this is a 3D graphics. 3D graphics. And the question asks us to find the image of such a box S. S is this box. Under the perspective projection with center of a projection at this point. So we know that now we need to put the things in a homogeneous coordinate. 现在要来处理这个，就是说我们要来做 perspective projection 的事情的时候，我们在三维坐标轴是不够的，我们必须要让它变成一个4×4的矩阵，在 homogeneous coordinates 的维度上面去操作，才能够完成完整的 perspective projection。那前面我们也给了perspective projection 的公式，那因为给定了这个给定了 D， 我们所谓的 center 这个位置 center 是0.0.D center. We are given the center coordinates being 0, 0, D. So here we know that D equals to 10, right? And then we make use of this matrix. Such a matrix P is a standard matrix for the perspective projection on homogeneous coordinates. So we can directly use minus 1 over D equals to minus 1 over 10 right here. And then this is the transformation on homogeneous coordinate, which is a 4×4 matrix now, even though we are working on just a 3D dimension figures. We still need the 4×4 operations, 4×4 matrix operations. And then for all of the 8 vertices, we also need to work on their corresponding homogeneous coordinates. And then to work on the homogeneous coordinates, we need to add fourth element 1 right here. So we are adding 1 on all of the 8 vertices. So there are 8 columns. So now I have a 4×4 matrix times a 4×8 matrix. So I can obtain the result like this. But now I'm still on the homogeneous coordinates. The next step is to transform it back to the 3-dimensional space. So it says that now we do not work on the we have already obtained the vertices after transformation and then on the homogeneous coordinates. But how do we retrieve the R3 space coordinates? After all, it is a 3-dimensional object. What I need is the vertices in its original R3 space. So so we are going to use the equation 1 again. Equation 1. Okay, equation 1 is this one. This is equation 1. Yeah, this is equation 1. I have the relationship x and capital X. X is equal to capital S divided by H. Y equals to capital Y divided by H. And Z equals to capital Z divided by H, where the capital X, Y, and Z are the values in the homogeneous coordinates. And X, the lower letter X and Y and Z are values from the original R3 space. So what matters are those H values. H values is as a result is the values right here. Those are H values. And we see that they are not 1 yet. So we need to convert them into 1. So like do the scaling and then make them 1. So in order to make the first column as something something something, 然后 and the fourth the fourth positions becomes 1。就我们要想办法让做一个 scaling 的动作，然后令第4个元素这个位置是一个1，对，因为前面那个比例相乘的关系是 equation 1，它的差别就是在于说h 这个位置是不是1。那如果要让第4个这个位置变成1的话，那么整个 column 它就需要乘以2，所以我们就得到了620，然后1写在这边，1不需要了，那 h 等于1了，对 h 也就 OK。然后再下一个，这边都是0.5的，所以呢，这边的每一个 all the columns right here multiply by 2, so that we can make the fourth entries becomes 1 times 2. And for the remaining 4 columns, I still want these positions that correspond to capital H. I still want them to become 1. So in order to do that, I need to first divide it by 0.6 and then multiply by 0.5. So divided by 6, multiplied by 5. So I will get 5, 8.3, 8.35, and then 1.7, 1.7, 0, and 0 right here. Okay, so we use the equation 1. We are able to convert the homogeneous coordinates back to the R3 coordinates. So here are some remarks. Here it says that the continuous movement of graphical 3D objects requires intensive computation with 4x4 matrices. 那这边说呢，为了要能够描述3D 物件的连续性动作，我们其实是需要4×4的矩阵。那4×4的矩阵，3×3是不够的，就我们需要多一个维度才能够去描述它的连续动作，包括它的 translation、transformation 等等。他这边说，特别是当我们要求它的表面的一些它的表面的纹理，还有它的光影看起来都要很逼真的时候，我们其实是需要相当密集的电脑运算。那这些电脑运算就是涉及很多matrix calculation. So here it says that high-end computer graphics boards will have 4x4 matrix operation, not 3x3 matrix operations, and the graphics algorithm embedded in their microchips and circuitry. Such boards can perform the billions of matrix multiplications per second needed for realistic color animation in 3D gaming programs. Okay, so inside those high-end computer graphics board 绘图卡上面的运算呢，都是要有就是快速的可以计算成千上万的这个矩阵相乘。OK， 那如果说是游戏的拿来做电脑游戏的这些绘图卡呢，更是要有这些功能，才有办法办到看这个3D 图像看起来是逼真的。Okay, so those are the first applications in the computer graphics. The second application we pick right here is in economics. 是经济学里面的一个应用，叫做 Leontief's input-output matrix 输入投入跟产出矩阵，那一样是一个很大的矩阵。This is again a very giant matrix to describe the relationship between input output for a nation. 那我们假设一个国家的经济体可以被分成好几个部门，那例如说它有制造部门，然后通讯部门、娱乐部门以及服务等等的产业。那假设说每一个部门呢，它都有全部的产出，每一年都有一个产出。那我们并且假设我们知道这些产出呢，它是用哪一些投入所交换所得来，是因为投入了哪些其他产业的资源，然后才使得某一个部门它得到了这些产出。那我们令所有的呃这些产出的价值被称作 price， 这些产出的 price。那 Leontief 是一个经济学家，然后也是一个诺贝尔经济学奖得主。他证明了下面的事情，他说呢，会存在一个均衡价格，就这个 price 呢，存在某一个价格，使得total output that can be assigned to the total output of the various sectors in such a way that the income of each sector exactly balance its expenses. 就是我们要找到为这些产出来找一个价格，然后使得它所投入的金额，也就是成本方面，它会刚好跟它的产出的价格是平衡的。那这件事情不是很困难，那我们虽然说这边讲的很抽象，而且这一页讲的基本上就是经济学的用语。So what has been described on this page is purely economic. So, but in terms of math, it's not hard. So we can look at the example and see how do we actually calculate such a matrix. But the difficult part is that we find the economic interpretation of such a matrix, even though we know exactly how to compute the solutions for such a table. But then to give a economic interpretation and then to make that interpretation meaningful is the difficult part. 就是难的是为这个 solution 以及它里面的数值做一个诠释的动作，而且这个诠释呢必须要有经济的意涵。OK，那这个就是 Leontief 他的贡献，他当然就是把这件事情用数学建模的方式所表达出来，然后呢算出解之后，并且把那个解也做了一个很好的诠释。So we are supposed an economy consists of coal, electric and steel sectors. 那假设我们现在讨论的是，就是燃料，然后电还有钢铁这三个部门。那假设我们在讨论的一部分经济，它里面就包含这三个而已。那实际上的一个国家来说，它可能会有50个部门，或是100个、150个，就是很多个部门。那这边是举一个简单的例子，所以只分成了3个部门。So this is just for an example. So that's why we only contains 3 sectors in this example. And the output of each sector is distributed among the various sectors as shown in table 1, where the entries in a column represent the fractional parts of sectors' total output. And to read this table, we could read okay, here it says that a sector looks down a column to see where its output goes. A sector, we look down a column to see where its output goes. and it looks across a row to see what you need as input. 所以我们读这个 table 的时候呢，是往下读一个 column，会看到这个 output 会跑去哪里，就是 coal 它的产出呢有留在自己产业的只有0%，然后0.6呢会去 electric 会去电相关的部门产业，然后0.4呢会跑去钢铁的产业。那 electric 这个部门，它的产出有0.4会跑去燃料这个产业，然后0.1会跑去 electric 这个产业，0.5会跑去 steel 这个产业。那钢铁所产出的东西，不管是主产品或是副产品，还有0.6会去 coal 这个产业，0.2会去 electric 这个产业，0.2会去 steel 这个产业。That's how you read the column. Okay, when we read down a column, we see where its output goes. And if we look across a row, we see what it needs as input. 那如果是我们要横向来读的话，就是说我们要生产1单位的 coal， 在 coal 这个部门呢，如果它的1单位经济产出，它就必须要有0.4来自于 electric， 然后0.6来自 steel 这个部门。那一样1单位的 electric 的 output， 它需要0.6来自 coal 的0.6的单位来自 coal， 然后0.1单位来自 electric， 0.2单位来自 steel。那 steel 这个部门，如果呢它要有1单位的产出，它是0.4单位要来自 coal， 0.5单位要来自 electric， 0.2单位要来自 steel。That's how we read such a table. And all right, so here it says, for instance, the first row of table 1 says that the coal receives 40% of electric output and 80% of the steel output. And since the respective values of the total outputs are PE and PS, here we let P to denote the total annual output, the price of the output in dollar value of coal, electric, and steel sectors, denoted by PC. C stands for coal, and then PE. E stands for electric. S stands for steel. And then we need to find the equilibrium price that makes each sector's income match its expenditures. So here, when we are talking about input output, we are talking about the quantity. We have not yet talked about its price. So then, in order to given this quantity, we are asked to compute the price of equilibrium price.